Well, whether we pay for it there or we pay for it. We'll get further into it.
Greetings, everyone. Happy Friday. We're going to kick off our Energy Bites. But first, let me tell you that next week we have 3 faculty director candidates coming to speak. So basically, you can just eat at work all next week. No need to bring anything. We're going to have a lunch on Monday, snacks on Tuesday, and snacks on Thursday, and then lunch on Friday for Energy Bites again. So we'll have a full packed schedule next week of seminars, so please try to come and attend if you can. So first up, we have Greg Miller. He's an Energy Graduate Group student as well as a researcher at the Center for Water and Energy Efficiency, and he's going to tell us about some of his research. And then next up, we have Curtis Harrington from the Cooling Center. All right.
Okay, can everyone hear me? Good. Okay, so hi, my name is Greg Miller. As Ellie said, I'm a first-year PhD student in the Energy Graduate Group and also have been working as a GSR in the Center for Water Energy Efficiency. So I've been really interested in the challenge of renewable energy integration and especially how we can use more flexible loads to integrate renewables on the grid. And I think we've heard a lot about how systems like HVAC and other systems can provide a lot of that flexibility that we're looking for. But one of the things that I've learned since coming here this year is that there's also huge potential within the water delivery network for this energy flexibility. About 20% of all electricity used in the state goes towards either pumping or heating water. So it's a big part of that picture. And before coming to Davis, I knew virtually nothing about how the water network actually worked. So today, part of what I'm going to do is just kind of walk you through what I've learned about the water system and help you all understand it in the way that I understand it and how it uses energy. I'll talk about the actual project that I'm working on with the team at SWE and some of the approaches that I'm taking. At this point, I don't really have any results to present to you. We're still in the midst of that project, and mostly what I've been doing is literature review and kind of defining the approach, but I'm going to walk through kind of where I'm at so far. So first off is understanding the energy intensity throughout the water network. So many of us here are energy people, and so what I'm going to do is, as I talk about the water system, talk about how energy is used throughout it, and also maybe use some analogies from the electric grid to explain kind of how the water network works. So the first aspect, there's four main aspects: supply, conveyance, distribution, and treatment. And you could kind of think of this in an electric grid analogy as like the generation, transmission, distribution, and I guess treatment doesn't really have an analogy. But with supply, unlike the electric grid where electricity supply and demand have to equal each other pretty much simultaneously because you can't store it, there's a lot of storage built into the water system. So when we're talking about water supply, that's fairly disconnected from the end-use demand patterns. And within the wholesale water purveyors who are actually supplying the water that we all drink are responding to a lot of different drivers. So of course they're thinking about maintaining long-term water supply so that we all have water to use into the future, but there's also a lot of other concerns that they have to think about, such as mitigating drought risk, maintaining riparian ecosystems, both upstream and downstream of reservoir projects and other supply outtakes. Controlling flooding is a big concern, earning hydroelectric revenue from some of these reservoirs, and also considering recreational uses of both downstream rivers, upstream lakes, and other things. So when we're talking about how they balance this supply system, there's a lot that goes into that. Now, there's three main sources of water where we get it from: surface water, groundwater, and desalted water. Surface water is a big source of this. This is rivers, lakes, all of that. And most of the energy load that goes into that is pumping it from that river or lake into the supply network. So the energy intensity of that is really based on elevation, but a lot of times, since the river or lake is at ground level, there's not a lot of pumping energy that necessarily goes into that. So surface water extraction is kind of the least energy intensive of all of these. Groundwater pumping, I think we've heard about. John Martindale talked a little bit about this for agricultural systems a few weeks back. But this basically is a lot of pumping energy, and it really depends on the depth of the groundwater that they're pumping out, and also the pressure that they have to maintain once they pump it out. So whether they have to, higher pressure systems require more energy. And groundwater is kind of, in the electric grid context, kind of like the flexible natural gas plant that's filling in the peaks and troughs of supply. So like when there's not enough surface water supply during certain seasons of the year, a lot of time groundwater kind of picks up the slack, and that's pumped especially a lot during certain seasons. And then desalted water is not really used as much, but it's basically, it could come either from brackish groundwater or from the ocean, and that involves not only pumping, but the energy load of desalinization. And so a lot of the energy intensity depends on how salty that water actually is and how much of that actually needs to be removed. So the next segment is conveyance, and this is the long distance kind of transmission of water across the state. And in California, we kind of have a special circumstance because there's two main drivers: that the fact that a lot of water supply is located in Northern California, while a lot of the water demand is located in Southern California, and then also that precipitation mostly happens in the winter and spring, and peak water demand is in the summer. So this necessitates huge conveyance projects that are basically transporting water like 1,000 miles across the state, over mountains, and also large amounts of reservoirs and storage built in so that they can store the water that comes down in the winter and spring for use in the summer and fall. So really a lot of the energy intensity comes from really big pumps. This is a picture of part of the state water project. So you can see that it's just like a big open canal that runs through the state. A lot of the energy intensity involved has to do with elevation changes, so both pumping it over mountains and then also recovering some of that energy when it comes down mountains through hydroelectricity. There's a lot of, for every gallon of water that's delivered at the end, with these big open troughs, there's a lot of evaporation, so more water has to be pumped in the first place. There's also leakage, whether the canal is lined with concrete or it's just dirt, and friction of the canal itself also contributes to the energy intensity of moving that water, although some of it is gravity fed. One thing about the flexibility of these energy demands is that the pumps that are used in some of these big projects are actually considered participating loads in the wholesale electricity market. So they actually are one of the few energy load sources that bid directly into CAISO wholesale markets and are kind of thus dispatched almost like a generator because it doesn't necessarily, because there's so much storage in the system, it doesn't really depend when exactly they're pumping as long as they're getting that water moved. The next system is the distribution. So this is once it actually gets to kind of the city level and has to move out to customers. And really the drivers here that distribution utilities think about is delivering clean, reliable, and affordable drinking water. And a lot of the energy intensity here, again, comes from pumps. And what they're using these pumps for is to pressurize the system. So that pressure helps actually move the water to the end use customer, and keeping a positive pressure in the pipes also prevents contaminants from seeping in, helping to fulfill that clean drinking water. And really, so again, the energy intensity of these pumps depends on the distance it's being pumped, the pressure. So agricultural systems have to be pressurized at a lower pressure than urban water systems, for example. Things like leakage, elevation change throughout the system, and also pipe friction. And thinking about the flexibility at the distribution level, sorry, this is kind of echoing or something. Thinking about the flexibility of energy demand at the distribution level, there's also a lot of water tanks, water towers and storage reservoirs that are built into the distribution center. But unlike reservoirs at the supply level, where they have to think a lot about flood control and river health and all these other recreational uses, a lot of these tanks and reservoirs don't have that concern, so really they're just optimized by the daily water demands, and so they have a little bit more flexibility to participate in those markets. And finally, is treatment, and treatment both happens at when water comes in from the conveyance network into the distribution level to make it safe for drinking, and also happens at the wastewater level once we've used that water and it needs to be treated into the environment or discharged. So a lot of the energy intensity for this, again, more pumping. Pumping is a theme throughout the whole water system, and also the treatment processes that are used. So the quality of the influent, the dirtier the water is, the more energy it takes to clean it. And also if you have a recycled water system, so if you're taking wastewater, cleaning it up and pumping it back into the distribution network, maybe for irrigation, that also adds some energy intensity, because typically wastewater treatment plants are located at a really low elevation relative to the rest of the system so that they can just be gravity fed, and then you have to pump all that water back uphill when you reuse it. And then also the level of treatment required. So there's kind of 4 different levels that I've learned about. The first is primary filtration, which is basically just screens that prevent solids from coming in, and that really requires no energy. That's just like a physical barrier. Secondary treatment is aeration, where you're basically pumping water up, and that helps, as I understand it, remove microbial content in the water. Tertiary treatment has to do with membrane filtration, so this is like reverse osmosis, so there's a lot of energy that goes into creating that pressure that actually drives water through that. And finally, disinfection is things like ozone and UV, and this is what's used to make it drinkable quality. And so generating ozone and also using UV light requires a lot of energy as well. So the cleaner you want the water, the more energy it requires. So that's kind of how the water system works, what I've learned about it so far, and how energy is actually used in the system. And next, I'm going to talk a little bit about the MNWD project, which is the actual CEC-funded project that I've been working on with people like Celia, Amanda, and Aaron, and Robert, and the rest of the SWE team. So MNWD stands for, this is I guess what we call it, I don't know if it's the official name, but is Molten Nagel Water District. So it's actually the pilot water district that we've been working with down in Southern California. And basically the goal of this project is to use software optimization to transform a water utility network into a energy load shift resource on the grid in a way that it can take advantage of the built-in storage, water tanks, and other parts of the system to shift loads to different parts of the day. And so we've been, well, not me, the rest of the team who knows all about the hydraulics of the water system and software engineering and all of that have been actually building this energy demand management system, which takes price signals from the markets and optimizes the system, like when you're filling your tanks and when you're running off gravity in order to reduce costs and also hopefully have some benefits to the grid. So those price signals that we're looking at are primarily at this point the demand response market at the wholesale level. So whether this utility could participate as a proxy demand resource in that level, but we're also, I think, maybe evolving to look at real-time pricing as well and what effect that could have, because with demand response, you're only getting compensated for curtailing energy demand and not shifting or increasing demand at beneficial times on the grid. For example, during the belly of the duct when there's a lot of solar. So with things like real-time pricing, you're getting compensated on both sides of that, because with a water system, whenever you're not pumping, you're going to have to make that up at some other time to fill your water tanks and make sure that you have enough water in the system to maintain that reliability. So that's the project that we're working with, and my kind of role in the project has been evaluating, once the software has determined what the optimal solution is for when to pump and when to not pump. My role has been to look at what the benefit or the effect of that is on the electric grid and different aspects of the energy transition. But first, before we look at those specific effects, one of the other things that we're trying to figure out is what is the actual statewide potential for this energy load shifting, not just at a single utility, but for all water utilities throughout the state. And so one of the problems working through now is how do you actually estimate what that potential is. So we're working with two main sources of data for this. One is the Public Water System Annual Report. So every water system in the state submits an annual report where they report things like monthly water deliveries by customer class, so like by residential, commercial, industrial, agricultural, how much water they deliver to them each month. And they also report how much water storage capacity, how many tanks they have, what that capacity is. And then we're also using the California Energy Data Request Program, which John also talked about during his presentation, in which we're able to, as an academic institution, directly request customer level utility data from the electric utilities. And so the goal would be to request hourly load data for all the water utilities that in selected territories. We may not need to look at every single, the electric demand of every single utility in the state, but select a certain population and scale that up statewide. Yeah.
Can you just I've never used that before,
That's a good question. I'm trying to find that out right now. I haven't actually started requesting this data yet. That's kind of my next step with this process. But what I understand is that it takes several months to request the data. You have to use Source, which is the secure computing environment, platform, and
you don't request it with, you're just saying you have to show that you're going to get.
I don't know how the actual data transfer process works. Like, I don't know if they're sending it over line or if they mail you a USB stick or something. I don't know if Robert knows. He's worked with this before.
IOUs are obligated process in terms of not quite much of the that data is allowed. Portal we set up. In many cases, the IOU will request a certain level of accuracy or certain level of data and a certain level of data protection from yourself. So that's the source environment that Greg is referring to. In particular, there's a certain level of accuracy, a certain magnitude of data that the customer is impacted. So an environment like storage begins to become necessary for that use access to that data and be protected for some of that data.
You have to negotiate with each
There is a, my understanding is there's
So that's the data that we're trying to work with to estimate this. And the kind of approach that we're estimating that we're going to take is that, so first using the water data, we know how much water they're delivering to each customer class, and there's also a set of kind of standard water demand curves throughout the day. So applying that data, we can reconstruct for each water utility what their hourly kind of demand curve looks like for water use. And then because we also know how much storage capacity that they have, we can estimate based on those water demand curves how long of a period they could actually run their system off of gravity and turn off their pumps. And then using that information and applying it to the electricity data that we have, we should be able to estimate how much energy they'll be able to curtail during a specific period, and then like how that would be shifted to a different part of the day. So that's the estimate that we're trying to come up with for how much statewide potential there is for this water utility load shifting. The final part of this is actually quantifying and this is I guess the main part of what I'm responsible for, but is quantifying the impacts of this load shifting on California's energy transition. So for this, there's kind of four main metrics that I'm thinking about assessing that are important. So how will load shifting affect cost of energy? How will it affect the Duct curve? How will it affect carbon emissions? And also how, in the long run, can it affect renewables integration on the grid? And these are all four kind of important policy objectives. So first, related to cost, we'll be doing an avoided cost assessment. And typically, a lot of times how this is done is through some sort of a economic dispatch and capacity expansion model of the grids here. In the short run, modeling how specific generators are actually dispatched in the wholesale market, and you know what their costs are, and you can estimate how those costs will change. And then capacity expansion has to do with what power plants are actually being built in the future, depending on how you shift loads and what power plants are needed to respond to that. And so the model that we'll be using is developed by E3 and used by the CPUC for a lot of these avoided cost assessments, which is called the avoided cost model or avoided cost calculator, which is built off of some of E3's dispatch models that they run. So that'll tell us things like deferred transmission and distribution costs, reduced costs from complying with RPS standards, all types of things like that. The next thing is the Duct curve, and everyone knows what the Duct curve is, but can anyone tell me like why we actually care about the Duct curve? Like, what are people concerned about the fact that this exists? Like, what are some of the things? Yeah, ramping's one of them. What else? There's three main things besides, well, two others besides ramping.
wasting solar.
Yeah, curtailment, wasting solar energy, and there's one more thing. Has to do with system reliability. So the main issues are ramping. So during this evening ramp, that's really hard for system operators to meet. Overgeneration and curtailment. Overgeneration has to do with more at the local level, the fact that on some specific distribution feeders, the amount of solar energy actually exceeds the amount of demand, and you're feeding demand back into the grid, which causes reliability issues. And then curtailment has to do with just the fact that we're wasting available solar capacity. We have to turn it off. And then system reliability, both from the standpoint that ISOs are kind of graded by their the amount that they're able to maintain frequency and reliability on the wholesale level. And these steep ramps are really hard for them to actually maintain stable frequency and voltage. So their scores have been decreasing recently, and so they're really concerned about that. And also with primary frequency response, so all the spinning generators on the grid have inertia, and whenever there's deviations in frequency, that inertia is like the primary response that allows the grid to remain stable. But when you have huge amounts of solar and you're getting rid of all of that inertia in the middle of the day, the grid's less able to respond to events that might interrupt that. So finally, my goal is to try to come up with some sort of metric that measures both how much load shifting is able to shift energy out of these, like this peak here, which is known as the kind of availability assessment hours. This is a metric that the ISO uses, and it's a pretty well-defined time period throughout the day, and how much energy we're able to shift into this belly, which again is also a really well-defined time period, and then also some sort of measure of the steepness of the ramp. So what I'm trying to do is come up with a metric that kind of combines all of that information, is able to assess how well a specific load shift profile actually addresses these issues with the duct curve. Can't really do anything with system reliability because that's really contingent on a lot of other factors, but trying to address ramping and overgeneration for sure. Looking at the short-run emissions impacts, those are all based on, and this is my second to last slide, these are all based on marginal emissions on the grid, so not what the average emission rate is, but what the emissions of the marginal power plant is that's actually going to be reduced in response to this load shifting. So there's two main approaches to calculating these marginal emissions. One is using least cost dispatch modeling, and so that's a simulation of the grid in which you're simulating what generators will actually drop off. And then there's also empirical regression models. With the dispatch models, these are things like mostly in California used through E3 again. There's clean net short accounting, which is used by utilities, and also the long-run marginal emissions rate, which is used in the avoided cost calculator. These are two separate measures of kind of marginal emissions on the grid. And with empirical regression models, this is basically, one approach is the marginal operating emissions rate, which comes out basically where you're regressing changes in emissions over changes in energy, and you're able to figure out, given like your amount of demand on the grid, what the marginal emissions rate should be. The other approach is an LMP-based approach where you assume that the cost of energy is based a lot on fuel costs, and you can estimate how much fuel is being burned based on that. So you're basically regressing emissions on LMP prices and able to estimate what those emissions will be based on what the LMP price is at any given moment. So we're still kind of settling on which of these, but I think we're maybe using the clean net short accounting, which is the one that actually the SCE's Clean Energy Optimization pilot's using to evaluate these impacts. Finally, looking at renewables integration, the question here is how well does a specific load shape or load shift shape actually match the renewable supply curve? So this picture is stolen from a paper, Callaway et al. 2018, which basically shows in yellow, this is the solar supply curve, blue is the wind supply curve, and then red is actually the demand profile of commercial lighting, and then the green is of residential lighting. So you can see just by looking at this that commercial lighting loads would be better at using solar energy than residential lighting loads, because the shape of that curve kind of matches better the shape of this, whereas this peak of residential lighting is really mismatched. So thinking about load shift curves as well and what that net shape looks like, you can come up with some sort of, working on trying to come up with some sort of metric that compares those shapes, and in the long run will tell you like how well does a specific load shape help integrate, let's say, solar energy or wind energy based on those average profiles. So with that, that's what I've been working on. I welcome any questions or discussion in the next couple minutes. Oh yeah. So this is just the y-axis is this labeled share of daily average production. It's just kind of a normalized measure of each of these. So rather than measuring all of these curves in megawatts, it's kind of normalizing them to a specific metric so that they can be compared. But it's mostly just think of it as like what the demand is at any given hour throughout the day.
It adds up to one.
Yeah, I don't know. I think what they're,
They're not.
yeah. I didn't make this chart, so I don't know exactly what they did, but it looks like some sort of average throughout the day, you know, how it accounts for each of these demands.
But they're all normalized into themselves, so it's not comparing.
Right, the magnitude, I would pay less attention to the magnitude and more just the shape. Yeah.
How short term
Well, so with the marginal emissions profile, that is a snapshot of the system as it exists today. So what you're capturing is if you shift loads around now, that's going to affect the existing portfolio of generation that's bidding into the market. So that tells you, like, you know, within the next year or so, because it takes several years to build a new generation plant, right? So with the existing fleet of generators, that short-term marginal emissions will tell you information about right now how much emissions are you going to be reducing. If you want to know more about, in the long run, how much emissions you're going to be reducing, that has to do with what plants are being retired, what plants are being built, and that's why the marginal emissions rate doesn't really capture that, because it's a snapshot of the current fleet and not necessarily future. And there are people working on like a marginal build emissions rate, which would capture some of that long run issues. Part of this, of thinking about renewables integration, is, you know, if we're going for 100% renewable grid, it'd be thinking about some of those questions of, if we're just building a bunch of solar, then this is like what that emissions rate would be, matching up those in the long run. But yeah, you can't really use long run emissions rates. The clean net short accounting that I talked about here is kind of the closest, according to like CPUC, is the closest thing that we have that the CPUC uses in terms as a like a long run emissions rate. And even though this one's called long run marginal emissions rate, they consider it to only be like good for the short term analysis. So.
For the real-time pricing portion, how do you
It depends, because so most loads on the distribution level can't participate directly in wholesale markets, so they'd have to go through a IOU program. So SCE, so this the MNWD service district actually straddles SDG&E and SCE territory, so that adds another layer of complexity, because some other pumps are on one rate schedule and some of them are different. But one of the utilities, and I think it's SCE, does have a retail level real-time pricing program for commercial users that they can participate in. So I think mostly what it is just a pass-through of the wholesale, like, locational marginal prices at that load. But I'm not entirely sure. But yeah, it's just based on, you know, every 5 minutes or hour throughout the day, how those prices fluctuate. And so you can use the day-ahead market to estimate ahead of time what those prices will be for the next day, and you can run an optimization. If you're a water utility, you could look at the day-ahead energy market, look at those prices, and the real-time prices won't match that exactly, but it'll give you a pretty good idea of how to optimize. I think so. So basically what clean net short is it measures how much of a specific utility's load is not met by renewables or base load. So it's any plant that, so you start with your utility curve, you subtract out renewable generation, and you subtract out base load, because base load isn't going to respond to fluctuation. So it's basically what you're left with is the average emissions of every dispatchable plant that utility is using to meet its load is kind of the measure. So it's kind of a combination of an average emissions factor and a marginal factor, but it's assuming that natural gas is on the margin. And I think that it does use different emissions rate based on, like, it's using the heat rate curves for the fleet of natural gas, which fluctuates throughout the day. It's combined cycle, combustion turbine, all of the whole mix.
Like a 20% difference in the efficiency.
Right, but I guess if the combined cycle plant was considered like a qualifying facility or something that is just must run all the time at a specific rate, that would be subtracted out and it wouldn't be part of that. Yeah. Sorry. Okay.
grab a sandwich? I'm gonna grab my power cord. Maybe that'll help. It's frozen. Oh, security alert. Oh.
Okay.
How do I get that though?
I gave you the corrupted file.
Yeah, must have been the virus I installed in my phone. It's already in the main.
You had the cursor up there, Alex.
Oh, did I?
You just gotta move it onto that screen.
Oh, the back down.
I can tell I'm Mac person. All right, you're good.
Thank you.
I will get the power cord in case it goes funky.
All right. Hello, I'm Curtis Harrington. I'm with the Cooling Center, and today I'm going to present on a project we just wrapped up for the EPIC program, looking at variable capacity heat pumps and the difference between system capacity and equipment capacity. So this is a project with the Electric Power Research Institute. We were a subcontractor looking at next generation HVAC technology. And so this is a very large scoping project. It had variable capacity heat pumps, ventilation, alternative refrigerants, thermostats, fault detection, all kinds of different things kind of boiled into one system, which we think kind of is the path forward for HVAC, moving forward for efficiency and air quality and so forth. But our role was a little bit smaller. The project overall had 3 phases. So there was 2 lab phases. The first lab phase looked at single zone systems. So single zone means basically you use all the ducting all the time versus multi-zone, which was the second phase, where you're able to include zoning equipment to kind of section off pieces of the ductwork and only supply air to certain parts of the house at a certain time. We also had a field component where we installed variable capacity heat pumps in the field and zoning equipment and looked at the performance. So again, UC Davis's role, we were a subcontractor, and we really focused on the impact of the duct system located in unconditioned space. So a lot of homes in California have ducts located in the attic. The attic's quite warm, so you can imagine if you're trying to cool your building and sending your air through a warm attic, there's some significant losses that can happen, and that's why ducts are insulated and so forth. But there's another level when you include variable capacity that we were interested in. What happens when you start to reduce that speed of the equipment, specifically on the duct system performance. And so we also looked at the impact of zoning controls on the performance of the duct system, and we developed a model of the equipment and the ducts so that we can look at it, parametric study analysis of different types of insulation or different climate zones. All right, so the way we did this lab testing is we took a duct system that was designed for a home in Sacramento by a contractor and put all those ducts in our outdoor chamber of our laboratory, along with the outdoor unit of the variable capacity heat pump. So essentially the ducts were in the same condition as the outdoor air. Attics are generally warmer than outdoor air, but sometimes ducts are located in a crawl space that might be a little cooler, so this is kind of an average condition that may make sense. There are the grills for the house as well. All right, so yeah, it's an actual 2-ton system design that we put in the lab. We use standard R6 ducting. Is this plugged in, this computer? Okay, because it just went like kind of dark. I'm wondering if it's going to go off on me. All right, R6 is kind of the Title 24 standard in many climate zones. And we sealed all the duct leakage to prevent the impacts of leakage. We're only looking at thermal performance of the ducts. Okay, so here's kind of the first set of results. This is looking at the equipment performance. So this is not including the ducts. It's just how the equipment performs. The DOE rates all these systems. If you're familiar with SEER ratings or EER for air conditioners, this is kind of similar to that. So it's just looking at the box. And what you see is that as speed is reduced in variable capacity systems, the performance improves significantly. And then as outdoor air temperature rises, the performance of the equipment goes down. Now, when you look at the duct system, we're using a term called delivery effectiveness. This is essentially how much cooling that you're making in your box in the attic actually makes it into the building where you're trying to cool it. So you can see at full speed, you're getting 70 to 80% of your cooling to the space. But as you start to reduce the speed of the equipment, you see some significant losses on the duct side. So we're getting, at a hot condition, don't know how to point here. At the hottest condition, you'll see that you're only getting 40% of the amount of cooling that you're producing in the unit actually into the building, so it's pretty significant. Okay, so in our lab, we were able to measure every individual duct run. So this is the delivery effectiveness of each grill that I showed in the picture. The grills are shown on the left there. As you can see, each grill is not treated equally. They have different performance. And what you'll also notice is that as you reduce speed, you change the balance of your system. So the amount of airflow through each grill, or relative amount of airflow, changes between the different ducts. And the performance is different between each of them. So now I'm going to talk about system COP, and this is the system performance. This is essentially, if you were going to include the equipment and the duct performance together into one metric, that's what we're doing here. So it describes the overall system performance of the equipment and ducts. And what you see is if you combine these, there's different optimal speeds depending on the temperature of your outdoor air or attic zone, as well, and temperature outside, and the speed of the equipment. So as you can see, at cooler temperatures at 85 degrees, the optimal speed to operate this equipment was about 60% capacity and airflow. But as you start to increase outdoor air temperature or duct zone temperature up to 95 degrees, you'll see that the optimal performance moved up towards 80%. And then at the hottest conditions that we tested, 105, 115, you'll see the optimal speed was to run this thing at 100% speed. So one of the main advantages of buying variable capacity systems is running it at part load, because you get a lot of efficiency gains. But as you can see here, if part load really doesn't help you at the hottest condition, there's some problems there, and you might not be getting the efficiency that you're expecting when you're investing in this kind of equipment. So next we added zoning equipment. So again, zoning on the air side in the attic, so you're able to deliver this capacity to different parts of the house, not delivering it to the entire house at once. We can significantly improve performance. So what you can see is the red line shows the delivery effectiveness of the duct system with zoning versus blue without at that hot condition. So you see, again, we're going down to 40% delivery effectiveness for the system without zoning, but we're able to maintain delivery effectiveness across all speeds of the equipment by including some kind of zoning equipment on the duct side. So you can see there's an optimization here. There's different duct zone, amounts of ducts open at different times. So there is an optimization algorithm that would have to be applied in order to achieve this type of efficiency, and that still needs to be worked out. This was done in the lab, so we were able to do things very precisely. But moving forward, that's something that needs to be looked at. Now, when you zone your system, you're going to have increased fan power because it's harder to push air through a smaller section of your ductwork. So if you include the increase in fan power, you'll see there's a slightly different result. While on the duct side, you're getting 95% more cooling delivered while using zoning at the low speed condition. The total system COP at high speed is essentially the same between zoned and unzoned systems. But at the lower speed conditions, you see significant improvement with zoning. At 60% speed, it's about 40 to 55% improved performance when you include zoning equipment on variable capacity systems. All right, so I mentioned that we did modeling of the duct system and the equipment. And so we used that model to run some different analysis looking at what if we added extra insulation on the system as opposed to zoning, because obviously insulation directly influences how much heat is lost through your ductwork. So we looked at insulation levels from R4, which was an older requirement of Title 24, all the way up to R12, which is not really an available product out there, but if you were to bury ducts in insulation or do something interesting like that, you could potentially get R12 on your duct. And then we also looked at typical R6 ducting with zoning controls. So as you can see, the zoning with R6 had the best performance across all speeds of the equipment. Interestingly, all of them had similar effectiveness at the high speed condition, which suggests, adding more insulation in the code on your duct system for single speed equipment is probably not going to get you very much in terms of efficiency. But when you're looking at variable capacity systems, you should consider adding insulation, especially to impact that part load condition. So R12 had significantly better performance at low speed. It was 20% higher effectiveness than R4. So that's another way you can address it, but clearly the R6 with zoning had the best performance. Yes?
Quick clarification. Yeah, clarification question.
Sure.
I understand that zoning means you can deliver air to different parts of your house without like. How does that actually improve efficiency?
So delivery effectiveness is the efficiency of the duct work, right? So there's two efficiencies. There's efficiency of the equipment, which I showed always improves by lowering speed. The duct work, when you lower speed, there's, and I guess I could have explained this better. Maybe this is a good opportunity. So when you lower the speed of equipment, essentially what happens is your heat exchangers become effectively oversized because there's less mass flow of refrigerant going through them. And so better performance on your heat exchanger gives you better equipment performance. Now, if you think of your duct system in the attic as a heat exchanger with the attic, you're trying to prevent heat exchange by adding insulation and trying to control that, but it's not perfect. As you reduce the speed of the airflow in that by not, without zoning, then you're improving the efficiency of that heat exchanger with the attic. So you're losing performance on your duct side. Now, if you're able to zone it, you have less surface area. You're making a smaller heat exchanger by only, delivering through a couple of ducts or a single duct instead of all 8 ducts. All right, so I mentioned attics are even hotter. So this is maybe possibly this result that we're showing is somewhat not getting the whole picture. I mean, attics are actually a little bit hotter. So we used our model to look at the impact of delivery effectiveness when the attic is higher than the outdoor air temperature. 11.2 degrees C must have come from some research that our grad student did. I'm not sure where that came from, actually. But essentially, attics, it's about 20 degrees higher, and so that's pretty reasonable for attics to get 20 degrees higher in outdoor air. So as you can see, the red line shows the typical, if the attic were the same temperature as the outdoor air, the performance. But if the attic is even higher, at a higher temperature, the situation gets even worse. You're only getting 22% of the cooling that you're paying for in the equipment out of the grills. Okay, so we took this whole lab test and results and took it out into the field. And so we recommended they put in zoning equipment so we could look at the impact of zoning on delivery effectiveness. So again, we're really interested in that particular component because the equipment performance is fairly well known and is easy to measure. So what we had to do was we had to measure the temperature at every grill. We had to measure the temperature and humidity at the equipment so you can separate the capacity going into the building through the grills versus the capacity produced in the equipment. You have to map the airflow for every grill, and so that shows a photo of the flow mapping process using a powered flow hood. And essentially we made all these little maps that we could basically monitor airflow using a pressure in the duct system. So a bunch of maps were made for the airflow and then used indoor and outdoor unit power for efficiency. So here's some of the results. This is the delivery effectiveness for one of the homes in the PG&E territory, showing all the different delivery effectiveness for every grill of that house during a situation where the equipment was running at 100% speed and all the ducts were open. So it's kind of like a single speed scenario or a full out scenario. And all I'm showing here is that the delivery effectiveness is significantly different between the different ducts. You have some running at 20%, which is terrible, right? And then, there's a cluster of them up here in the 60 to 80% range. So again, we kind of verified what we found in the lab. Each duct is kind of their own little system, and they behave differently.
Is that correlated to distance from the RTU itself?
Next slide is the correlation. Well, one of the correlations, there might be more. I didn't find any others that were this compelling. So what we did was we looked at, it seems that velocity is a good indicator of that performance. Velocity in a duct system changes all the time because there's branches, and so what we're looking at is the final branch velocity. This is the velocity just before it reaches the grill, so the final duct run. Say you have an 8-inch, just the final velocity there. And what you can see is there's a really strong correlation between that final velocity and the performance or the delivery effectiveness of your duct. The really poor performing ducts had really low velocities at the end of the branch versus the better performing ones that were up here. So this makes it a little easier. We can just kind of design for having higher velocities in the duct. It makes it easier on HVAC contractors. You don't have to think about, the surface area necessarily. This might be a good way to kind of design a system just focusing on velocities. Typical maximum velocities allowed in residential systems is about 600 feet per minute to avoid kind of high noise and vibration in the duct system. So if you were to design a perfect duct system to meet 600 feet per minute on every one of your grills, you'd have really good delivery effectiveness up here. But if you put variable capacity system on that same duct system and you reduce the speed by 50%, you're immediately losing 30% of your efficiency, 30% of the cooling is lost to the attic. So.
Is there any
Not that I'm aware of.
because they're
I mean, there's Manual J, and Manual J tries to
it's like a
get.
recommendation though.
Yeah, I don't think there's a code and like a compliance requirement.
I don't think that historically the Energy Commission has recognized that low velocities can consume excess energy because you generally think, oh, my fan will have less resistance, I'll get.
Sure.
And in fact, the Energy Commission may essentially work against itself because it keeps changing lowering the amount of watts per CFM your fan.
So people oversize their duct system.
Yeah.
Sure. Yeah, that's a good point. Okay. I thought I added animations to this, but we'll just go for it. This is another plot showing the same house with all the grills here at a situation where it's 100% speed and it's all the ducts are open. At 175 minutes, one of the zones shut down. So what happens is, and this green line shows the airflow of the unit. When that system or that zone shut off, so the master bedroom and another bedroom shut off, you'll see there was a slight dip in the airflow, but essentially the airflow remained constant throughout this process. So that meant the airflow in these remaining ducts immediately went up. They went up by about 25% in velocity, and there was an immediate, on average, 10% increase in efficiency system COP. So this is kind of a real-time demonstration of the impact of duct velocity. So we had demonstration homes in San Diego Gas and Electric Territory, SoCal Edison, and PG&E. So this shows the full data set for the San Diego Gas and Electric home, showing system capacity in orange, or system COP in orange, and equipment COP in orange and system COP in blue. As you can see, the system COP at 5.2 was really good. That's a very good system COP, or equipment COP, and the system COP was 3.4. So this was the overall result of all the data we collected. It looks like the duct effective or delivery effectiveness was about 65%. So it wasn't terrible. These houses all had zoning, and this particular house had R8 ducting. So it was kind of a good situation, but the zoning was definitely not optimized using the algorithms we could potentially develop through this research. So it was just kind of doing its normal zoning operation, which isn't looking at efficiency. It's more about comfort. And then on the heating side, you'll see again the equipment COP was fairly good at 3.8. Heating COPs are generally slightly lower than cooling COPs for heat pumps, so that was expected. And then the system COP was 2.6. Again, the delivery effectiveness was similar. It was about 68% for the heating side. So overall, it looks like the delivery effectiveness was pretty good, but there is some room for improvement, and it was not optimized. All right, so general takeaways from the project. We think variable capacity systems have a lot of potential. You can control the ratio of dehumidification and sensible cooling by separately controlling the indoor fan and the compressor speed. So they allow you to do that, and so in hot, dry climates, you don't need as much dehumidification. You could potentially do more sensible cooling and improve performance that way. So that's a great opportunity that variable capacity systems allow. The ducts significantly impact performance of variable capacity systems, particularly at low speed when you'd expect your equipment to be performing the best. So as a consumer, if you know enough to be dangerous, you might think, oh, I'll just run at low speed all the time and I'll be pretty good. But what we've shown is that, depending on the conditions outside, you may want to rethink your strategy for controls. And then duct location and installation will impact the optimized control. Again, the climate zone or the amount of insulation would change how you would potentially control the airflow through your duct system. Because again, at 85%, or at 85 degrees, you saw that the optimal speed of the equipment was lower, so you potentially wouldn't want to zone the equipment down in that case, but it really depends. And including those control algorithms would be a pretty big effort. So that's something we're interested in tackling at some point, but it's not really available on the market. So we think the best solution is variable capacity systems with zoning would give you the best performance for heat pumps in residential in California. This combination addresses the equipment and duct performance, so it takes into account how your equipment's performing and your duct system and is able to modulate accordingly. It facilitates energy demand response programs, so typically for variable capacity systems, a demand response would mean turning your system down to low speed as opposed to turning it off, because they have the capability of shedding load, but still providing some cooling to the building. Obviously, we showed that you would get a big performance hit if you do that during a demand response when your attic is warm. We were just talking about the peak demand is in the afternoon. Your attic maintains that heat throughout the evening hours. So by including zoning, you can have a demand response and maintain efficiency. And then lastly, we showed that increasing duct insulation will also improve variable capacity performance. And will also reduce those interactions with the attic. That's what I got. Are there any questions?
Have variable systems,
Variable capacity is, I think, sought, and then there's a sticker shock with them. So people end up going to something else, like maybe a two-speed. A lot of two-speed systems are being installed. I don't have any numbers. This is just anecdotal. But I would say that they are not, they're probably 10% of the HVAC market, I would imagine, or less, because of the price.
It's gotta be like 1%.
Yeah. People do zoning, even with single-speed equipment. One of our affiliates, Velara, formerly Butler, they did all of these homes in Sacramento, and they include zoning in every one of their homes. For top floor and bottom floor, there's a pretty significant temperature difference between the two and load. So they generally install 2 zones in that scenario. And now they're doing townhouses where they have 3 zones with a single-speed equipment. And they have to get pretty fancy with how they do the design, the ductwork design. But as far as controls, it's fairly simple. You have a thermostat upstairs. It calls for cooling, and it asks the equipment to turn on, and the damper opens. But there's not a consideration for temperature in the attic or things like that. Yes?
Was this all controlled for duct leakage percentage? Were they all at 5% or something?
In the homes, they were measured. They were not sealed it wasn't part of the protocol to seal these ducts. They had to meet the Title 24 HERS rating requirement. I think it's 15% of airflow.
So it wouldn't be that much, most likely.
No, and that would be boiled into this result because we weren't looking at that in particular. But when you put the zoning really close to the equipment, even though the pressure rises in the system for that small segment, essentially it works out that you don't have increased percent leakage when you zone it. Now, if you put zoning at the grill and you shut a grill off, then you'd have increased leakage because your whole duct is pressurized. As long as you get the zoning closer to the plenum.
So it's at the plenum itself that you have like.
As close as
dampers.
possible, yeah.
Okay. So what does the topology of the multi-zone system look like? Like, is there one main duct coming out of the RTU that then branches off into different zones, or is it like different ducts from the unit?
Oh, yeah, so there's generally the equipment, and then there's a large plenum where they do distribution. They cut holes in it and run ducts. In a zoning scenario, they may have, say, a large duct coming off that plenum, and then a zone damper, and then it distributes into 3 or 4 ducts, and then another one and another one of those. So, yeah, generally there's a large duct, and then it distributes into dampers and zones.
So if you turn
Yeah.
on
Mm-hmm.
speed unit
So it depends on the zone control that's being applied. The zone controller we used in this is very flexible, probably as flexible as you can get. So you're able to weight a zone. So if it calls for cooling, it'll call for, it says, hey, I need cooling in this zone. But the controller that acts like the thermostat, it's a mediator. So the thermostats talk to this controller, and the controller looks like the thermostat to the unit. It'll say, oh, it needs cooling, 100% cooling, but it'll say, but it's only weighted at 25% of the weight. So it'll only ask for 25% capacity. It'll open the damper, and that thing will run at low speed. So it really depends on the zone controls and the algorithms used. In this case, we had a lot of flexibility, and so we tried to control the zoning in order to maximize, try to run those algorithms. Like, essentially what we would like to do is run, if you're running at 50% speed, use 50% of your ductwork. It ends up actually working out really easily that way, because attics are generally warmer than 85 degrees or 95 degrees. So we kind of just went towards the condition of the hotter condition where you want to run your ducts at the highest velocity as possible. So that's what we strived for in this, but it was a bit challenging. Yep. There were 3 homes, and they were all 4-ton systems. Some were 2-story. One was a single-story house, 1,800 square feet. It's kind of funny. They all just were 4-ton. I don't know. There wasn't much thought, I feel like, going into those numbers, because the project just hired the local contractor, and they did a like-for-like kind of swap out. So, yeah. Does that answer the question? Okay.
As far as the controls, where's the sensor?
So there's a zone control. There's a thermostat in every zone, saying if it needs cooling or heating, and there's a zone controller that interprets all of these signals. It says, oh, zone 1 needs cooling, zone 3 needs cooling. Let's open 1 and 3 damper and apply this amount of capacity to that. So it makes there's some algorithm. I mean, there's some ability to adjust the decision making there. And this was also, we looked at dual fuel, so there was a time when you might want to switch to gas furnace as opposed to heat pump. So there's like an optimal point for efficiency, there's an optimal point for cost for the customer. Those are different points. So like when the temperature outside gets to 40 degrees or below, just use natural gas. Like, don't use the heat pump. And that's based on the efficiency and the cost of electricity. So that all happens in the zone control board. All right. Thanks very much. Yeah, I was just gonna talk to you. It's like it's not even there.
Yeah, you
great.
forget about it, which is nice.
Yeah.
As long as you put down low, it seems to be working. some echo if you have.
Oh, really? Oh. Do you like take your own and like?
Well, I was like, hey, you can use my house.
Find out.
One of the I'm trying to avoid it during the study because you don't want things changing. The control for everything by measuring everything, so it doesn't really matter because the goal isn't to find the best way to program this particular unit. It's more of general, like, okay, well, let's increase what this is something I did, and you can see the data showing you that it's improving performance. I did little tweaks, but I was kind of sensitive to it, so I probably continued to mess around. Or I'd think about it way longer. Kids' room was like blowing up.
What's the phase velocity? So because Greg was asking, because he wasn't asking me the question, like, why is this? You know, also the biggest part was the fact that the slower fan speed and you shut off.
That's another way to describe it. Your air sits in the attic longer.
Yeah,
That's one way I think it's.
Yeah.
So I tried something. I've said that a few times to try to get people to understand it. And I've used that one with like. That's the one that makes the most sense. Like a train. There's like time is not moving closer to the heat exchanger, right? And it's like, sure, it isn't, but it kind of is.
So help me.
Do you not like the explanation of the bigger heat exchanger?
I don't.
You don't?
No. It's not as intuitive. He's not a PhD student in mechanics. No. What makes way more sense
That's
is
just general.
exactly. It doesn't stay and stew in that heat.
Yeah, you don't want your cold air sitting in the attic longer than it needs to push it through as fast as you can.
Get it to your face.
cold.
All right.
Thanks for my.
That poor thing, it died.
Well, yeah, I had no idea. The battery's not that long.
Well, it was also recording that other guy.
Oh, so it took more
running the
power?
recording software. Oh, yeah.
No, it was. It was like probably 15 when I started, so I was like, I was thinking it was going to go on the Glad you said something.
I have to get that video.
Hey, so yeah, you want to take it later?
Yeah, I'll take it.
Okay.
Yes, go ahead, please. Enjoy.
I don't want to say he's single. I was out to like, no, I'm not playing goalie. I spent 5 years of my life just doing it all the time. I want to play soccer. He's like, okay, how do I want to play out? Like, yeah, he does. When it's not close. Blast it up.
You can never ever have too many computers because there's always a problem. Right? So we've been using classic area.
Sorry, I fucked up on that.
I haven't done my kind of study.
Who say
I
that?
haven't done my progress assessment yet.
Only
I'm
had
gonna
6
do it next
weeks.
week. I know, but I think that's pretty cool.
I know, as long as you get it done.
Double digits now with our